Dr. Geronimo Villanueva, a research assistant professor at the Catholic University, right here, and resident at the NASA Goddard Space Flight Center. His talk will be Discovery of an Ancient Ocean on Mars, Probing the Planet's Past and Current Habitability. Welcome, Dr. Villanova.
Okay, so hi to everybody and welcome to Catholic University. So we're in this exciting conference, and as we got it from these initial talks, this is the advocate community for us going to Mars. And it's fascinating to be here. It's great that you all join us. This is the force we need. My talk is going to be about what we know about science from the science side of past and current habitability, and as being a driver for exploration of Mars. And I've given a story which I think is important. You know, when we went to the moon and then we had the Viking missions, we were actually very committed to the Mars exploration program, but then the Viking went and didn't find life, which was one of the elements. It was in the late 70s. And then from there, the Mars exploration program actually died for a long time. It was actually in a very low phase. And with the latest discoveries, being happening, like the discoveries of ancient water, perhaps on Mars, methane, organics, and stuff. The concept of habitability and is driving more the exploration of Mars. So I think this community, together with these new discoveries, are embracing us for sending humans to Mars. So when I start, I'm going to talk a little bit about Mars. I'd like to give a story. What do we know about Mars, the history, and I give you a sense of the whole context. So we know the Big Bang, 13.7 billion years, the beginning of the universe, start being developed, somewhat dying, forming new material. And then we are here in the present, the expanding universe. To give you a sense, our Mars and our planet start to form in this sense. So from 4.7 billion years of that whole time range, Mars has been forming to what it is right now, together with our planet. And in order to understand habitability, we need to understand what are the primordial blocks that went into the planet to define is it habitable or not habitable. How do you define habitability? So we know that 4.6 billion years ago, there was a cloud of gas. In the inner part, we had this proto-sun. And then there was something like a magic line called a frost line. This is the line that divides when water is in the vapor phase or is in the solid phase. So here it condenses, and then if you go beyond here, you have methane. And then here inside you have water in the vapor form. So if you're forming planets, you're gonna coalesce a lot of solid rock and ices and form a lot of icy bodies within this line. A lot of methane here, a lot of ice. But here you'll find a lot of rocks. You won't find a lot of vapor. So if you keep building the solar system that way, you form the rocky planets, which are within this fictitious line, the frost line. It's so dramatic in our solar system. All of these are rocky planets, and these are the gas giants. So the key thing is, if you find water on Jupiter, that's not important. I mean, it's primordial. It was given from the get-go. It's relevant, but it's not the big thing. If you find methane in Pluto, it's interesting, but it's primordial. It's not relevant. When you find water or methane in a rocky planet, that's important because it indicates that something that has been abnormal into the development of the planet. It's something that should be in very trace amounts. So when we look for habitability, we're looking for those things which are rare. And in a rocky planet, water and organics are rare, just because of this formation process. And I always like to make this analogy because we know our planet is blue, and we think it's a blue ocean planet. But at the end of the day, we are a rocky planet. We are a rock solid, and if you put all the water together, that's the amount of water we have. That we can quantify in the surface. So we are a rocky planet, and Mars is a rocky planet, and the amount of water is small. So a small amounts of water can define habitability in a solar system. So we live in a rocky planet, so our definition of what is habitable is based on that. So there are 4 rocky planets in our solar system: Mercury, Venus, Earth, and Mars. And as you get closer to the sun, it gets hot. Further out, it gets cold. And it's a very anthropocentric definition, but habitability is defined a region here called a habitable zone, and we are the only ones in our solar system that are in a habitable zone. And what is a habitable zone? It's a region in a solar system, in a planetary system, that the surface of the planet will maintain liquid water. Obviously, we are the only ones, unfortunately. So you're thinking, what do we care about Mars then, if it's not habitable on the surface? So all our prospects of habitability on Mars are below the surface. This is what we think liquid water will remain in subsurface. You can have it in brines in the surface, but they're not going to be very habitable as we know it. But if you go penetrate below the surface, the habitability pressures and temperatures are going to rise, and then Mars becomes the only habitable rocky planet in the solar system. That's why when you want to explore the solar system, Mars is such an important element. Venus is a good laboratory for science, and you can go to the moons of Enceladus or Jupiter, Pluto. They're interesting from a scientific point of view. But Mars is so important because of the component of habitability below the surface and for human exploration as a rocky planet. So the two planets are actually very similar in some aspects. So the obliquity of the planet is 25 degrees right now, and it is 23 for Mars. It means the seasons of Mars are similar to our planet. The summer and winter typically are very close in the sense of contrast between winter and summer. The day of Mars, 24.7 hours. Day of Mars, 24 hours. Mars is smaller, has gravity 38% of Earth, and is further away from the sun, so it gets less sunlight. So from there, we are similar. We have Mars has polar caps, Earth has polar caps. But the main difference is in the atmosphere. This is what defines the two planets. If you look at the CO2 content, it's trace amounts. Actually, it's going higher because of our greenhouse effect. But on Mars, it's 95%. We are nitrogen and oxygen atmosphere. So when you look at an atmosphere which is so built in CO2, we think an atmosphere has been combusted. Everything has been given and transformed into CO2. So there's nothing going on the planet. It looks like a dead planet from that sense in some way. When you look at nitrogen and oxygen, you're looking at a lot more chemistry, and we know biology is a big driver for this oxygen that we have in our own planet. But the key thing between the two planets actually is in the size. And in this case, size matters. So radius of Mars is half of the radius of Earth. And the history of the two planets were defined by these initial sizes. And now I'll tell you a bit about the two histories, how the two planets evolved because of the difference in size. So you don't have to remember the names, but just to give you a sense. So in Earth, the history is defined, for 4.6 up to the present, in these four areas: Hadean, Archean, Proterozoic, and Paleozoic. These are defined all by biology. Biology defines our eras and all the geological times in our planet. When you look at Mars, obviously we don't know its life there, so everything is defined by geology, and there are three eras: Noachian, Hesperian, and Amazonian. So let's see what happened in these two planets, how they evolved. So on early Earth, we had geological activity. We had an early Earth which was not a very habitable place, I would say. You had surface water and heavy bore magma. It was very acidic. It was not the best place to be, actually. The planet started to stabilize, develop plate tectonics, circulation of the crust and the mantle, iron-rich oceans, no atmospheric oxygen still, but it's a planet which is interesting, habitable. And that time, microbial life started. And they were talking about very simple life. And we think we had around that time. And it lasted for a long time. Actually, for billions of years, we only had very simple life in our planet. And then we had a surface-rich ocean. We still had an oxygen-poor atmosphere. From that sense, the two planets could be looking similar. But microbial life was all the time there. And now, boom, multicellular life started, then the whole evolution, and then we have humans. So we went from a very, steady state, habitable place, and when everything became habitable, we got life, and then multicellular life started much later. So you're thinking, if this happened on Earth, what was happening on Mars? The two planets were similar. So actually, Mars was similar to Earth. Actually, they were very similar at the beginning. We had geological activity, a hot core with clays and probably surface water, ideas maybe some oceans. This is the place where we like Mars. This is the most habitable time on Mars. We call it Noachian. This is the best time to be on Mars. But the problem is that the planets start to build, volcanic activity, climate change. The planet was getting this acidic environment, and then the planet started to die. It's a smaller planet, started to cool faster than our planet, never developed plate tectonics. So we had this burst of late volcanic activity. The planet started to get the red color, but the planet was dying geologically. Our planet was still alive. So what's driving is a driving force. So, life arose during this, 3-point-something billion years, and Mars was there at a similar time. That would be the best time to think that Mars something developed. But the planet died, and we don't know where it was. There are some theories which are not proven, but they say that even the inner core of the planet is actually a rock. So the planet seems to be like geologically dead in many aspects. That's why it's made of CO2. People don't see volcanic activity, and we have minimum geological activity. So if life arose, it could have been during the Noachian time. And because it never developed plate tectonics, that life could have been preserved below the surface, and it could be there right now. But the conditions were different in the two planets. So the questions there are now are, was Mars ever habitable? In the sense that we know it, not in a little area, but in the whole sense of the planet. How much water did the planet actually have? Was more like this or more like this? And if some of them survive below the surface, if some of those subsurface areas are still there. So I will tell you a little bit about what are we doing as scientists, NASA and our agencies, to look for what is going on right now. Current activity, geology, biology, anything. So on Earth, anything that produces a chemical imbalance is a way to test for activity. So for example, on Earth, methane is a power biomarker, more than 90% is. So in order to deliver those things to Earth, you can have meteorites, comet impacts. You could have below the surface a process called serpentinization that it will, rock and very little temperature, not very high temperature, serpentine, rock, and water in contact will produce methane. So that's a geological process to produce organics on the planet. And again, in the subsurface, the same process. You see the gas, you know what is going on there. You could have very simple archaea biology producing the methane. The key thing is this. If you see a gas like methane, it would mean four things. Something hit the planet, which is actually pretty cool. You can have geology or you have biology. So in order to search for activity, you look for these chemical tracers, things that are in imbalance with the atmosphere. Methane is one of them. So the key thing is, if you're looking for activity, you're looking for these molecules, like methane for biology, or hydrogen sulfide, or SO2, CO2 for volcanic hydrothermal activity. And if you have a subsurface water reservoir, and then it gets in contact with the atmosphere, opens up, and you can release this methane. You are testing for habitability below the surface. That's the way we are doing this. So the key thing also is interesting. When you have this gas methane, above 60 kilometers, it will get photolyzed and produce other molecules like methyl and hydrogen. You can also look for these compounds. If you go more in the lower hemisphere, it will oxidize with oxygen and form formaldehyde. So you're seeing much more molecules. You're looking at much suite of things. Electrochemistry with hydrogen peroxide, methane, and you produce another suite of molecules. So the key thing is, if you're looking for activity, you have all these tracers you can look for. So now we have a much more complete suite of things you can search, and that's what we've been trying to do. So what happened? In 2009, we discovered the biomarker methane on Mars. And so you're thinking, it would mean one of these things. And what we saw actually was very interesting. We saw these plumes of methane. We have the water maps and the methane maps, and they were very localized. They were not everywhere. The fact that they were so localized were pointing that maybe these were coming from below the surface in a plume way, like what we're talking about. So they would open the idea that maybe geology, biology was active on the planet. And that was a big drive. That was 2009, like 6 years ago. And it defined many instruments are being developed for Curiosity, actually. Curiosity got a methane sampler, and some of the missions that I'm going to be talking a bit later. So the possibility of releases could be there, something below the surface. Actually, we got a lot of attention. I love this tabloid and Sun. NASA reveals life on Mars. Obviously, we never say that, but it's obviously you get a sense of what is the big thing about Mars and methane. So when we think about biology, we're not thinking about very complex biology. We're thinking about if you have radioactive minerals, which we know are present on Mars, water we know is present on Mars, carbon dioxide, a simple archaea biology as a simple life we had in our planet, it will produce methane as a product. So this is one of the hypotheses being developed as a way to produce methane. So where on Mars we think habitability could be there? So we have this area called a photic zone, which are a few centimeters. This area was being radiated by a lot of radiation, and typically life doesn't like this. There's some stream of funds allow that, but it's not the best place. You have the seasonal sublimation area, the temperature will penetrate and will produce this. And then you have the permafrost, which is ice and rock. And then you have the subpermafrost, where we think the liquid water will be there. So as you can see, we're talking about several kilometers deep. And all the rovers cannot drill that deep. But this idea of the kilometers move up and down depending on which model you consider. Some people even say that you can actually be, a meter or 2 meters, you could be probing the subpermafrost, where liquid water will be there. So the question is, was Mars actually ever habitable? We know that maybe there, something may be happening right now, but the question is, was it ever habitable? Was ever, we really know that it was globally habitable or not. So we did a measurement recently, and the trick is based on this. If you break water into the three components, one of them could have hydrogen in a heavy form called deuterium. So it's water with a heavy hydrogen called deuterium. So if you break water and this doesn't do very well, but the things are, the atoms are coming out of the atmosphere. So what happens is the light form of hydrogen will escape faster than the heavy form. You have the heavy form in the lower part of the atmosphere, survives more, than the lighter form. If you leave that running for 4.5 billion years, you will escape a lot of the light form of hydrogen. So you're slowly going to be enriching the atmosphere with the heavy form. You are enriching the atmosphere in deuterium and depleting in hydrogen. So actually, people have probed the meteorites, they measure that the D/H, this is the ratio between the two forms of hydrogen, on Mars 4.5 billion years ago, when the planet formed, was actually pretty close to 1.275 the terrestrial value. B small means Earth oceans. So it says that the water on Mars was exactly the same in the isotopic signature as our planet, which is actually interesting. Curiosity, just published last year, probed that at the Gale crater, they just drilled some sample. They were simply something that was 3 billion years old. They already saw that the D/H actually raised to 3. So it went from 1 to 3. It means that it was losing a lot of water. Already in those 1.5 billion years, it lost a lot of water. So the question is, what is the value right now? And you will say, we should know that. We don't know. So there were no water of this D/H until now. And we wanted to know, we can use that number to probe how much water the planet had, how much water lost. And this is the key what we've been doing. Other test you can do is this, which is actually pretty cool. Imagine you have the atmosphere escaping the water, as I was telling you, and you're enriching the D/H of water, or let's say to a factor of 7 the Earth value. It's being losing the water all the time. If you have water here below the surface, and it's being protected for 4.5 billion years, that water will be like the primordial water. So you have very low D/H. So in order to prove there is anything connecting to the atmosphere, you can look for signatures of changing the D/H. So if there is anything connecting with the surface, the place where we think habitable is, we may see a drop in the D/H. So we have two ways. The D/H has a very important element. It tells you how much water was lost, and it tells you that maybe you can search for habitability below the surface. So we embark, and we use 3 telescopes and 2 spacecraft. These are 2 in Hawaii, 1 in Chile, to make measurements of this quantity D/H on the planet Mars, to see what is there, what is, what's going on. And actually, just to bore you a little bit about the spectra, the lines just to tell you, the detections are very confident. These peaks here, your red peaks, this is water, the heavy water on Mars. These are very bright lines. And these other ones here, this is water on Mars, the regular water. So we can actually probe the 2 waters very precisely. We can get very nice maps. And we did. So this was published in Science this March. And we got these maps of the heavy form of water the heavy form of water and the regular. We see more water in the north. We know that's polar cap being released in water. We get these 2 maps. But the key thing is making the ratio. And remember, the D/H is something that's been losing for 4.5 billion years. It should be constant across the planet. So when I did the ratio of the 2 maps, I got these color things. And I have to say, the first time I did this map, I was very surprised. I think something was wrong, because remember, isotopic signatures don't change. They are telling you something about 4.5 billion years. So they shouldn't change on short time scales like days, hours, and within geography. And when I was seeing all this red, it changed from 1 to 10 across the planet. So I'm thinking, wow, this is very strange. And I was wondering what's going on. Actually, Curiosity is here at the Gale crater. And these guys measure value around 6, and our number is around there. It was the same number. So the numbers were right. We knew the numbers were right. But the question is, what does this number mean? And I will tell you a bit about what this number means. So when we published this, also, we got a lot of media attention because there is a quantity that we pull out from those maps. And it's about the common water, primordial water that the planet had. So the story is like this. So we have the equator of the planet. This is the winter hemisphere. There may be some subsurface reservoirs of water here. We have the polar caps, the summer polar cap, where almost all the water is located on the planet. Then that water is released into the atmosphere, And then we get the two forms of water, and it gives you a number around 7, the terrestrial value. This is the greenish color we saw across the planet. It tells you that's the typical value of the atmosphere. Okay, and then if we go to the winter hemisphere, we're seeing that we're condensing one of the heavy form faster. So the fact that we saw a very low number there is just climatology. It doesn't tell you anything about evolution. But we can identify that. It was actually a good thing. Some of the low values in the volcanic district will associate again with cloud formation, not evolutionary. Interesting, but not relevant. The key thing was this. The number, since we know the number 7 there from the atmosphere, we know the number in the pole. So we know the main reservoir of water, what is the D over H of water. And what we can do with that? We can do this. So now we can plot time here before present, and this will give you the D over H, okay? We have the polar D over H, atmospheric D over H, and this big variability just by climatology. So we have this meteoritic record, which is 4.5 billion years there. So we have a line there. And then curiosity came in between, put a number there, 3 billion years. And we saw that the D over H was increasing. It means that Mars was losing a lot of water with time, actually. The D over H has been going up with time. So you can play with a little toy model, and you can make this red line there. And it tells you that the Mars was been losing water at this rate. Once you know the D over H, you can make this quantity, which is what we care actually, is the blue number, the blue trace. The blue trace is just a form of the red trace. It tells you that if this is the water right now, that the water 4.5 billion years was 6 times what is right now. So Mars lost 87% of this water right now. So it lost a lot of water. So now we know how much water the planet had. It's actually pretty cool. We know we can test habitability in the past, 4.5 million years. We can actually map it in time, how habitability was moving with time. So that's what we did. So we got all the water of Mars from the polar caps, multiplied over 6.5. We melted and let it rain on the planet, and voila, you make a big ocean on the planet. So if all the water, you multiply by 6.5, and you will build an ocean. Actually, that ocean you see shrinking with time, but it will create a big volume of water. We don't know how long that water was in the liquid form in that state, but we're saying something that was there for 20% of the planet was covered by water with this amount of water. It's bigger than the Arctic Ocean. So this is a big amount of water being on the planet. Habitability in the past was very, very probable. So if some of that water survived, and it went below the surface, you may have a very habitable planet. So the key thing is that we can quantify that Mars was habitable. Actually, it was very habitable in the past, in the Noachian, the same time that life started on our planet. So the conclusions about this are this. So we see the strong anomalies. We can quantify the water loss. They quantify that it will mean that a nation ocean on Mars was bigger than the Arctic Ocean, and it was actually consistent with some geology forms on the surface of the planet. So it would cover up to 19% of the water of the planet. The question is how long that water was in the liquid form. Maybe it was icy for a long time. Maybe it was wet for a long time. We know it was wet, but we don't know how long was that habitable place there. So the next step for science purposes, for us, is to go and see if some of these low D over H things we saw are related to some sort of habitable niches. We saw these plumes of methane, we saw this decrease of D over H, so maybe there's something going on below the surface that is habitable for us, not only for exploration, but from the scientific purpose, but also from the exploration point of view. Just to tell a bit about the timeline, what is going to happen. We have a launch date of ExoMars 2016. It's a European Space Agency mission and an InSight Discovery mission. The InSight mission will try to actually probe what is the interior part of the planet. We don't know. We really want to know the inner part of the planet. It's the NASA mission. March 2018 or 2020, the next phase of the rover, the ExoMars mission, is going to send a rover and drill on the planet up to 1 meter. The James Webb Observatory will be launched. Has a Mars program. And then we have the Mars 2020. So these are the main Mars missions, robotic exploration of the planet happening. Actually, the ExoMars mission is a pretty cool mission. It has a full orbiter looking for methane, organics, and all these things I was telling you about the D over H. And it's going to be pretty amazing for that purpose. It has a lander, and then it has a rover that can drill very deep. And the idea is to drill enough that you can actually probe the subsurface of the planet to see what was there for some time. And then the James Webb actually is a pretty cool, because it's going to be located in a particular orbit, will do very excellent science for Mars, and it will allow to look for organics and the overage very precisely. So that's all. Thank you. Yes.
I was curious, many years ago, Odyssey mapped subsurface water on Mars.
Yes.
Okay. How does your estimate of 6 times the current water square with the amount of subsurface water inferred from Odyssey? And are they in the same places? And do you have any overage data from that archaic water, say, Curiosity or Polar Lander, will they show up?
So that's a good question. So Mars Odyssey actually was probing hydrogen. And we don't know what form is hydrogen. It could be in a different form, not water. So what I did is infer from that hydrogen how much water was there. The key thing, so it's hydrogen. That hydrogen is only up to 2 meters. We don't know even deeper than that. And that water, if it's locked below the surface, it should have the primordial D over H enrichment. So it should be the same value as our planet, because it has not been escaping the atmosphere. So the only way we can multiply the water, we can only multiply the water that's been in contact with the atmosphere. So I'm talking about anything that is in the polar caps or is in the surface. And that number we kind of know very well. Yes.
Could you comment on future habitability of Mars? Specifically, is there enough water on Mars that in a few centuries with terraforming one could have water on the surface again if one were to also create an atmosphere? Would have to be that to be imported from somewhere else through comets or however? And also, given the absence of plate tectonics and of a magnetic field, what are the challenges of retaining that water and that atmosphere if one could terraform Mars in the future?
Correct. So it's a very good question. So Mars lost the water because it's a small planet, and escape is pretty easy. And you can see the plot. It's going to keep losing the water with time. But we're talking about geological times, 4.5 billion years. So even if you terraform it, it would be there. I mean, we wouldn't notice. I mean, it would be a very long time. Mars actually has a lot of water. I mean, it's mainly locked in the polar caps. We don't know very well about the regolith, what we call the upper part of the surface. But if you put all the water, and Mars will be a sphere, it's up to 30 meters of water. So it's a lot of water. So I think for exploration purposes, if you can harvest some of that water, that should be, my impression, should be sufficient. Yeah.
Yeah, a few months ago, some researchers announced the discovery of subsurface glaciers on Mars in mid-latitudes, 40-degree latitude range. And that would imply that there's more water on Mars now than had previously been believed, which if you then multiply by 6 or 7, would be much more water in the past. Can you comment on the relevance of this data?
Yeah, so Mars, I mean, one of the interesting things about Mars doesn't have a moon like our planet. So it means the obliquity changes like crazy. The planet has been moving the obliquity. So what it means that the polar caps on Mars, they were sometimes looking at the sun, and they were not the polar caps. They were completely sublime. And that happens pretty fast. It means that all the water in the surface is being vaporized. So if you have a glacier at 40 degrees right now, some time ago was in the polar cap. That's what I'm trying to say. The key thing is any water that is locked below the surface will not have an enrichment of the D over H. Only the water that's been interacting with the atmosphere will produce this slow enhancement of the deuterium. Because if water you have a lock and is in solid phase, it will always maintain the D over H. So you cannot multiply the water in the glaciers below the surface by 6.5. Only the water which is interacting with the atmosphere. Nevertheless, I agree. Our inventory of water is very limited because it's based on the polar caps and the regolith. Anything below the surface we don't know. And as he was commenting, the hydrogen and now the glaciers, those are things that are helping us. And I'm pretty confident that below the surface of Mars is a lot of water because Mars, had cracks, never developed plate tectonics. That water has to go somewhere, and I'm pretty confident there's a lot of water stored below the surface.